Yeah, we can start. Hello, everyone. Good evening. Science knows no country because knowledge belongs to humanity and is the torch that illuminates the world. These are the words quoted by the famous scientist Louis Pasteur. And with a similar motto, Shasthra Snehi, in association with Zeroing In, an amateur astronomers organization based in Kerala, brings before you the Science Week. I am Arunas, co-founder of Shasthra Snehi. On behalf of the entire team, extend a hearty welcome to all those who have taken the time out to join with us for this inaugural event. Well, I would like to just brief you about all the three of our organization contributing to this event. Shasthra Snehi is a non-governmental organization focusing on the scientific empowerment of the society. We try our best to give the best knowledge to people in a simple, attractive and legible way. Now talking about Zeroing In, which is one among our collaborators. Zeroing In is a student-led science podcast channel curating conversation with eminent scientists and technocrats. Our other collaborator, Astro Kerala, is an independent non-profit scientific and educational organization devoted to popularize astronomy and space science. Seeing that our motto complements with each other, the three organizations had joined their hand together to bring this event before you, general public. This week, we have got a lot of events in store for you and hope that you all would have the same amount of enthusiasm until the end of the week. The registration for all those events are open right now, and you can head on to our website www.shastrasnehi.com/scienceweek for the more details. Moving on with our program for today, it's my privilege to introduce you our speaker, the famous theoretical physicist and the person who is known for his work on topological string theory. It is indeed an honor to welcome Dr. Rajesh Gopakumar, the director and the senior professor of International Center for Theoretical Sciences, Tata Institute of Fundamental Research, Bengaluru, for the interactive session. Sir, we are indeed very much honored to have you with us today. So without any further delay, we can move on to the session with Sir. I'm sure you all have been eagerly waiting to hear from him. Over to Gautam and Naman for beginning the session. Naman will give a more detailed description about the professor, and we can start. Naman, over to you.
Thanks a lot, Arun. Hello, everyone, and really great to see you all here joining us today. So I just want to start with a brief introduction of Professor Gopakumar, and then perhaps we can begin. So Professor Gopakumar does not really need an introduction, but just to do the formalities, I'd say that Professor Gopakumar did his bachelor's studies at the Indian Institute of Technology in Kanpur and went on to pursue his doctoral work at Princeton University under Professor David Gross. Thereafter, he pursued his postdoctoral fellowships at the University of California, Santa Barbara and at Harvard University before moving to India in 2001 as an associate professor at the Harish Chandra Research Institute in Allahabad, where he was working till 2015. Thereafter, he moved to the International Center for Theoretical Physics, a part of the Tata Institute of Fundamental Research at Bangalore, and assumed the role of the center director shortly after joining. Professor Gopakumar has had an exceptionally illustrious career and an inspirational journey over the years, with major milestones studded in his career that very few are able to command. He has received numerous coveted laurels in some ways that still fall short of doing complete justice to his pursuit of excellence, be it in the pivotal academic works that he has pursued and produced and still has been actively contributing to, which are now considered as seminal pieces in the field, or be it in terms of his leadership, which has been momentous for the academia scene in India. And we have the ICTS as a clear example for that among his multiple other contributions to the field at large. We're extremely elated to have you here with us, Professor, and we look forward to our discussion. We would just like to take this opportunity to thank the students, researchers, and professors who have taken their time out to join us today. On behalf of the organizers, we'd request you to keep writing in your questions in the chat box, and we can address those through the course of the discussion, or you can ask these questions when your name is called out as and when. Your hosts for today for this discussion would be Gautam Krishna, a part of Astro Kerala and Shasthra Snehi, and who is currently pursuing his research in astronomy and astrophysics from the Jagiellonian University in Krakow, Poland. And I am Naman Jain from Zeroing In, the Science Podcast channel. Without further ado, let's jump into Zeroing In with Professor Rajesh Gopakumar. Good morning, sir, and really happy to have you here. So Yes, I mean, I believe I can just start with asking you this idea that we've been discussing over a little bit, and we really wanted to ask you this. So it's a general saying, right, that if you are able to like explain a concept to a 10-year-old, then you understand it clearly. But we believe it's definitely not true for someone who's doing string theory. So would you like to have a starting comment on that, just on a lighter note?
Firstly, let me thank all of you for inviting me to this inaugural meeting of your three combined organizations. It's always very very heartening to see young people such as yourself with a passion for science and for communicating that to others in your generation and your peers, and the hard work that you've put in to put together a meeting like this. So my congratulations to Shasthra Snehi zeroing in, as well as Astro Kerala for a very successful event that you have lined up for your inaugural activity. So firstly, yes, and about the particular question that you asked. It's of course, I mean, that's definitely a very nice thought, and in some ways it is something that one should aim towards. One should sort of be a benchmark. Understanding, of course, is many layered, and there are several layers at which you can understand and explain, and so both explanation and understanding can come in different at different levels of granularity, and I think definitely there should be a very broad level which is perhaps accessible to a 10-year-old, that one should be able to at least lay out what are the central questions or ideas in the subject that one is studying, and that is something that is, I think, a challenge. It's not an easy. It's of course very difficult, and I have a son who is actually now 14, but I have been talking to him since he was 10 or before about many things, about the things I do. So I do know firsthand the challenges of doing something like this. But I would definitely say, for something like, if there are any 10-year-olds amongst you here in the audience, I would definitely say string theory is a subject which is trying to understand the nature of what is the force of gravity which all of you feel when you fall down or throw a ball. What is the underlying, really the underlying nature of this force? Why is there such a force of gravity? Why does it take on such a why is it prevalent all over the universe, and how did it play a role in the beginning of the universe and in such extreme objects like black holes that we know are there in the universe? So maybe that would be a very nutshell way of at least explaining the motivations for the subject, and perhaps one can develop on that idea and talk more about what string theory does. But yes, but I like the spirit. I think you have to take the question in the right spirit and not perhaps too literally. I mean, because after all, if you really want to explain it, you would need to go into the more detailed and often mathematical explanations.
Precisely, sir. I believe, yeah, I mean, for string theory, all of us believe that it's one of the most, the theories that are on the verge of the abstraction of mathematics as well as the intuition of physics. So it just kind of always is a question on how to explain it to a young generation in some sense, because we don't touch it in college and in graduate courses as well. So yeah, over to Gautam for the next question, I believe.
Yes. Good evening, sir. I hope you're doing good. And I would like to go back to your life. So the question I would like to ask is, where did it all begin? Like, did you already had an idea that you will be pursuing this particular area of research, or something or someone influenced you, or what do you say, to influence you to follow this particular path? How did it all begin?
So I would say that I was always interested in science, and in school, I think my interest in science grew out of from an interest in chemistry, in playing with chemicals and doing various fun chemical experiments at home when I could try to get hold of some day-to-day chemicals like vinegar and baking soda and things like that, starting with something like that, and then and then I think the fact that all of chemistry is based on atoms was and the structure of atoms was something very striking to me when I encountered it, and then as I tried to sort of learn more about that, I realized that underlying, to really understand what atoms are, you need to know physics and quantum mechanics. I was also in parallel interested in mathematics, and so in any case, I think around class 9 or 10, I think I was very clear in my mind that I would study either physics or mathematics. So at least at that level, I knew what I wanted to do. I didn't, of course, know about string theory then, and this was 1983, 84, 85, and that's a long time ago. And string theory, actually, it was 1984 that string theory really emerged worldwide as a potential, very serious candidate for understanding the quantum theory of gravity. So anyway, I wouldn't have really heard of it at that time. But I did read about it in 1986 or something in some Scientific American articles. But at that time I was not so narrowly thinking. I was thinking about physics and mathematics very broadly. I think the writings of the book Ideas and Opinions by Einstein made a very big impact on me. I remember the program of Cosmos by Carl Sagan that I watched on television. Actually, I watched before it came on television. It was shown in the planetarium in Kolkata, which I had gone and watched. It was wonderful because they showed it 6 days consecutively, 2 episodes each, 6-7 days. So within a week, it was a very deep immersion, and it was really inspiring. Carl Sagan. I don't know how many of you have gotten to see the old version of Cosmos, but it's certainly very inspiring, and I would urge anyone to actually view that. And then I think when I was in school, I heard people like Roger Penrose actually had come to Calcutta, and in 1986, I think he had come to Calcutta, and in the planetarium again had given a talk on black holes and so on. So these were all very, I had read about Penrose and Hawking at that time, and Hawking's very remarkable results. And so these were, so I was broadly attracted to all these areas in physics and theoretical physics and mathematics. And I think in my undergraduate years that just deepened, and I still think of myself as a broad theoretical physicist, and string theory is just one of the most exciting areas in theoretical physics, I feel. So that's what I'm choosing to concentrate on. But I think, and we can talk about it later, but I think string theory is a very broad framework with which to understand many things, and not just actually about quantum gravity, which I mentioned earlier. So, but in my early days, I think I was just very broadly interested in physics and mathematics. I had some good classmates and friends in my school years who were also interested in mathematics, physics, all sorts of exciting things. I think at that stage, one should not narrow oneself. One should just be excited by whatever is intellectually very stimulating, and I think I had good friends. We used to do mathematical puzzles and other things together, and enjoyed those things, and read many books and shared books with each other. The internet was not there, so it was more difficult to get hold of good books and things, but and information. But that was fine, I think, and And then in college, of course, I had many influences, very good teachers, very brilliant classmates, and so on. And I think they played a very big role in my evolution as a scientist. So especially many of the teachers, I think it was when I went to IIT Kanpur that I really saw physics teachers who were passionate and really understood the basics and could explain that and could transmit the excitement of the subject. So that was amazing.
Great, Professor. The one, especially with the teacher, really resonated with me because it was like a seventh grade physics teacher that actually inspired me to also pursue the area of physics. So that resonated well with me. Thank you. And I think I will just hand it over to Naman for now.
Yeah, so I mean, I would just like to mention as a trivia for the audience that Professor Gopakumar secured the first rank in the IIT JEE exam, which is now so popular in the popular culture. But I mean, as the backdrop, I just wanted to ask, how is this transition from this student who is extremely excited about all these areas of physics to a life of theoretical physicist? I mean, this transition into this life, and how did you think, or your ideas kind of get elaborated from there on?
Yeah, no, I mean, I think it's a very good question because one doesn't know. I mean, at that time, one just dreams and one has some very exciting thoughts. And but one is not sure one can find one's way through all the technical hurdles and all the other things that are there before But I think I mean, of course, each stage, the transitions are non-trivial, and one has to, going from school to a place like an undergraduate institution with a lot of very good and very demanding teachers and students and classmates and everything. That's one transition. And then the transition from being a student to being a researcher in your PhD, making that transition when you are no longer doing courses and trying to just learn some things that are there in textbooks, but actually doing new things and thinking of new things. That's another transition. And so on and so forth. There are indeed many transitions one has to go through. But I mean, personally, looking back, I feel the life of a theoretical physicist that I'm leading right now is what I always dreamt of doing, and it is more or less what I imagined, and I think I was, I think, mostly sustained by just by the excitement of learning and doing learning and thinking about so many new ideas and concepts. I think that excitement, that is what carries you through all the difficult periods that are there, and difficult periods are part of life, and I think one should sort of embrace that. One should not shy away from it. That's necessary in some ways to grow, but yeah, that will happen. But if you have a thread carrying a thread of continuity, taking you so that you still are connected to that boy or that child you were in class 8 or 9, I think you will not lose your way.
That's a very valuable advice. Yeah.
So I remember, I don't remember the exact words, but I once read in a documentary about, I watched a documentary in which one of the persons was saying, life is about carrying a message from the child that you were to the old person that you will be, and not to lose the message along the way. So you are really carrying a message from your past into your future. You have to make sure you don't lose that message.
Yeah, Gautam, would you like to?
Yeah, sure. So, regarding your work of interest, that is the string theory, again, I will have to confess that I am not very well versed in that area. It's very, very basics for me. But as a trivial question, I mean, as a basic question that I have heard from many people, is it true that there are like multiple dimensions considered in string theory? And if that's the case, then what exactly is the physical significance, if there is any physical significance for these dimensions? Could you just talk about that a little bit?
Yeah, no, definitely. I think the simplest. So string theory is a very broad framework, like I said. So there are many, so to say, solutions of string theory, many possible avatars in that string theory can take. And each of these manifestations, the simplest set of ways in which string theory can connect with our four-dimensional world, at least as originally imagined, requires you to have a sort of four-dimensional space-time and something like 6 internal directions, which, of course, since you're not seeing them, they have to be at a very small scale. This, of course, is not an idea that is new, that string theory introduced. It actually dates back to some years after Einstein studied the general relativity, where he described gravity in terms of the properties of space and time. And there were these physicists, Kaluza and Klein, who realized that Einstein's theory can be generalized to include electromagnetism, that is Maxwell's electromagnetism, which at that time was the only other fundamental force other than gravity that was known. This was before we knew of radioactivity and the strong interactions and so on. So electromagnetism and gravity were considered the two fundamental forces of nature, and Kaluza and Klein at least realized that there was a way, there was a very relatively simple way in which you could also get electromagnetism if you added an extra dimension, which was like a circle. And the size of that circle, if it was sufficiently small, you would not, so you could still geometrize both electricity, magnetism, as well as gravity, but in terms of now a 5-dimensional space-time, and with one extra direction being like a circle, which is of a radius small enough that you do not observe it, at least in, of course, not only day-to-day life, but also in any of the current experiments. But perhaps there will be, you have to, depending on the scale of that dimension, you can probe it if you are sufficiently energetic. And the analogy that is given is perhaps something many of you may have heard of, that supposing I have like a small a cylinder or a small straw, then from a distance the straw looks like a line, but if I come very close to it, then I see that there is one extra direction. But if I were normally, it depends on the size of my perception. If I were an ant, I would be able to perceive the straw, and because its dimensions are comparable to my dimensions. But if I were an elephant, then the straw or the tube will be essentially like a string or a thread. So it will look one-dimensional. So even though it's secretly two-dimensional, it looks one-dimensional at very long distances, or if you're viewing it from afar. So that is the philosophy of these extra dimensions, that and so they actually play a role. And in string theory, in these simplest avatars that I mentioned, these extra dimensions the novelty. They are more complicated than just being a circle. They are more complicated, higher dimensional spaces, but their properties can give rise to many of the forces. In fact, ideally, you can get all the forces of nature, including the strong and the weak interactions, through some of these geometrical constructions. So that is one way in which people were hoping to connect string theory to some of the forces that you know already in particle physics. But I should stress that in recent years, string theory, people have found many more solutions of string theory, and I think we have only scratched the surface, and there are probably many other ways in which string theory can connect to the forces of particle physics. And there is a certain constraint in string theory, which for a consistent string theory, that normally you satisfy it by demanding that the space-time be 10-dimensional, but that's not the only way it can be satisfied. You can have some other fields turned on, and in which case the space-time may not be fully 10-dimensional. And especially now that we have realized that our space-time is not really flat on the cosmological scales. It is what is called a de Sitter universe, or a universe in which there is a cosmological constant, positive cosmological constant, or dark energy sometimes, as it is called. So we've begun to, I think, learn both from observations as well as from the theory that maybe we need to think of a broader set of solutions within which string theory can describe the universe that we see. So extra dimensions in many ways are part of string theory, and if they are in the simplest way, you might observe them. If string theory realizes these extra dimensions as the way to get forces that we see, then we may hopefully see them one day in signatures of these extra dimensions in accelerators or other probes. Just like when you go down to the scale of an ant, you can see the extra dimension by sufficiently energetic particles. You should be able to probe the extra dimensions and see other signatures of it. So hopefully if that is the way that string theory connects to the particle physics world, then one day we will hopefully see it. So it's very much part of string theory, but there may be other ways in which string theory may also connect. So I just wanted to add that caution that, often it is associated with all these extra dimensions, and people are thinking about things not necessarily tethered to 4 dimensions. And I think that's useful because it opens up your the number of possibilities. And we do not yet know. We don't have any evidence that the world is only 4-dimensional. So we have only bounds. We can say that up to this scale, we know that there are no extra dimensions, but at the level at which gravity comes in, the extra scales can be very small, and you would not have measured them yet.
This was a beautifully intuitive explanation. I mean, multiple ideas came to my head while you were talking about it. One went in the direction of, for instance, Flatland, which is this small book that's written, which also talks about. Yeah. And then on the other end, there is this idea of fractals that also comes up. That no matter how much you go in, there's this constant recurring sequences and so on. But would you also like to talk about perhaps any experiments in this direction that are already being taken up, or is there like an experimental realization that is being worked about, or how do we look further into the string theory in some sense, like the way further in some sense?
Yeah, so one of the most promising, I think, avenues is in cosmology. Where you might see signatures from the early universe, which might tell you the kind of fields and that were there in the early universe, which perhaps drove this initial growth phase called inflation. So those fields should come from string theory if indeed the universe did go through an inflationary phase. And you see, you would see the remnants of that imprinted on the microwave background and also in the large scale structure of the universe in terms of the distribution of galaxies and so on. So from these very early signatures, which actually come from quantum fluctuations of the field in the very early times, which have been, so to say, frozen. And therefore, we see still the effects. They're frozen and they're magnified. So this is how we can see the effects of quantum effects in very early universe right now. And from those, I think I am hopeful that we will learn as these experiments get better and better. We'll learn more about the nature of the fields that were there and how exactly string theory string theory can realize those kind of fields. Because as of now, string theory admits a large number of possibilities, and I think we will need guidance from experiment to know which possibility indeed is realized in nature. And cosmology is one of those ways. In particle physics, also maybe through understanding some of the new particles we hope will be there, like behind dark matter, and even understanding dark energy in some fundamental way might also tell you the kind of these are all potential experimental inputs that can help us to sort of to tell us which avatar of string theory we really need to be focusing on to connect with the early universe. So that's, I think, the situation right now. But there is another aspect of string theory in recent years, which is connecting actually to string theory as an alternative to what is called quantum field theory, which is been in a sense the pillar of one of the other pillars of 20th century physics, apart from the general theory of relativity. The quantum field theory is what has described successfully quantum electrodynamics, quantum chromodynamics, the electroweak interactions, etc. So, but string theory seems to give an alternative way of looking at quantum field theory. And I had recently given a talk to an undergraduate meeting very much like yours, held by students at the Chennai Mathematics Institute, and they had an event called Tessellate last month, I think, and I gave a talk which is there on YouTube called Why Strings, and I tried to tell why strings actually arise from the old ideas of Faraday about lines of force in electrodynamics. And actually, it's a refinement of those ideas that are now also playing a role in understanding how strings can connect to quantum field theories, describing the strong interactions and so on. So that's another whole aspect of string theory that has come to the forefront in the last 2 decades, and which is one of the very exciting frontiers of string theory.
So, can I take over?
Just add that that's an area where I also think, because string-like excitations are very natural in nature. They arise in many contexts, like in the strong interactions, or even in the electromagnetic interactions. In some sense, the lines of force that Faraday drew are really some kind of very diffuse strings. But in the strong interactions, they really become tightly bundled up into a real thick, tensionful string, but it's there in superconductors. It's there in, even recently you see these vortex-like structures in superconductors or in turbulence. I think the presence of extended string-like excitations is very ubiquitous in nature. And so string theory is the framework that tells you how to describe such excitation. So it's not only in the context of gravity and cosmology that we should really think of strings. So that's one of the points I was emphasizing in this talk for those who are interested.
Okay, so Professor, one of the questions that I would like to ask is, you are a theoretical physicist, right? So when working on a theory, when can we say that working on a theory ends? When the experiment actually demonstrate that theory, or if it's some other theory which will be in align with the theory that you are working on right now? And should one keep checking on the consistency of these theories now and then?
Yes, of course. So theorists usually try to address certain outstanding questions which we don't know satisfactory answers to. And that may require sometimes building a new framework, and that's what string theory does. But most often, and 95% of theorists actually are not doing exactly that. They are finding new phenomena which have unexplained, which are unexplained, and trying to describe in terms of already existing theories and frameworks also. So people, for instance, who are finding very complex behaviors in some materials, or some people who are studying the properties of turbulence, which is again a very unsolved topic of physics, just turbulent flows in fluids which arise in many places, or people who are studying things involving black holes in the astrophysical realm. They are trying to not necessarily build up a theory, but use often existing theories to see whether they're adequate to describe these phenomena. And that, of course, has a dual purpose. Therefore, if it succeeds, that means you are, and most of the time it does, and most of the time the existing theoretical frameworks have been successful in explaining some phenomenon, that a new phenomenon that you see, or a new material that you properties that you discover, etc. So that is a test of the existing theory, like you said. So it's a way of testing those theories, and at the same time it increases your explanatory power of the universe, and the different, and each such new discovery kind of pushes the frontiers of the theory, the domain that theory is explaining is expanded, and so in some sense theories are constantly being existing theories. So I would say in 20th century physics, there is the framework of quantum mechanics, or more completely quantum field theory that I mentioned, that describes many things in both at the level of particle nuclear physics, but also is a description for so-called many-body systems, like in condensed matter physics, and quantum field theory is by now a very powerful framework describing many different areas in physics. And then there is, of course, a general relativity which describes gravity at in the most sophisticated classical description, and you have to use some of these both in say astrophysical or cosmological situation. So you're all the time testing these two major theories, and of course classical mechanics and so on within their domain of explanation, where relativistic effects or quantum effects are unimportant, they're also being tested all the time by the devices we build, the things we by new explorations of complex systems, which are just complex systems at the classical level. In soft matter and so on, there are many ideas which basically use just statistical mechanics, thermodynamics. So all these frameworks are constantly being tested because you're coming up with new things, to new phenomena. Experimentalists are always on the lookout for finding new, interesting, unexplained phenomena, and it's always a challenge to the theory. So in that sense, I think you're doing that all the time, and you're not doing it just as a way of in a routine checkup way. Each time you're doing it in a new, interesting direction, and you don't know a priori whether it will work or not, but more often than not it works. And if it seriously doesn't work, then that's also a challenge, because then you have to think of what it is that will explain. So yes, so that's sort of how it the interaction of theory and experiment. So in that sense, there's no end to the theory.
That's a wonderful insight, sir. Yeah, I mean, I believe I would like to change tracks a little bit and ask you, if it's okay, about the ideas or your perspectives about the state of fundamental research in India, and broadly how the education works in India. It's not really so direct to see that it is focusing on research, for instance, as we see even in the scenario that there are most of the colleges in India are dedicated to science or engineering colleges. So, I mean, given that you have had these perspectives from a global perspective and over the years also in India, how do you see the state, and how do you understand this can be made better or different, if at all there is a change needed?
Yeah, no, I think there's a vast room for improvement. I think the situation now that I see compared to when I was when I was in school and going for an undergraduate education has changed a lot for the positive. There are many institutions like these, many more institutions doing science research and undergraduate teaching. The ICERs and the NICER, and then even many of the central universities now have a master's program, integrated master's 5-year program. So there are, I think, many more people who have been also trained in good institutions who are taking up faculty positions in many of these new institutions or new programs in existing places. So I think the overall quality of undergraduate education in India has improved in science, and there are many more options. But I think it's still very small for a country of the size of India, 1.4 billion. There's still the number of people who want to go in for sciences is still a very small fraction, because I think there is still a lot of societal pressure to go into engineering or medicine or some management or some very safe option like that. I think that should change, as science should be viewed as a very critical resource and an asset to the training of any person in the modern world. I think, in fact, our constitution is one of the few that is probably the only one that emphasizes the cultivation of a scientific temper and so on. So I think this was put at center stage, but we need to do much more to create that scientific temper, I think, in the country. And this should, of course, start even at the school level, where I think curiosity is not often encouraged. It is not often nurtured in schools, and school teachers themselves, I think, are often not motivated enough or in teaching science. They teach it in a very kind of a way which sort of puts off students who don't really understand what they're just thrown a lot of facts and they're just told to memorize it or absorb it, even mathematics. And so all these things, I think every subject has its barriers, its learning barriers. And I think pedagogy is about finding ways to take people over those barriers and in a way which you can, such that they don't get traumatized by it or they don't get totally put off from the subject. And so I think there is a lot of scope. I think people, there are many institutions, many individuals trying to reach out to even schools and demonstrate that the fun of physics, through simple science experiments. I think Dr. Arvind Gupta has had this web page and a YouTube channel and so on, where he shows how with very simple materials you can really demonstrate very non-trivial physical properties, or even come up with questions which don't have very good answers just based on everyday phenomena. So I think that inquiry spirit to get children to question why things are happening around them, even simple phenomena, you can always find some very interesting things happening that you normally don't observe. But just teaching children how to observe and trying to frame questions and having some channel by which they can ask and sort of, so to say, do research at that young level. I think you're never too young to do research. It may not be in the formalized, channelized way in which, of course, the scientific research happens, but anyone can do research in terms of just questioning things, trying to find explanations, both in mathematics, in physics. Even in mathematics, you can play around with numbers and come up with patterns, try to explain them. In physics, you can try to open a tap and see how the water flows, and do lots of things just in your house or every day. I think that somehow I think we need to inculcate more of that at the school level. And at the undergraduate level, I see a positive thing, but I hope it will grow.
Okay. Professor, so I get asked this question a lot, and right now I am going to shoot that same question at you. That is, how does one justify the financial investments that is being given into the field of theoretical or fundamental or astro, so to speak? How can we justify these financial investments that is being given to these fields, since they don't seem to be showing any direct contribution to the society that we live in? So, any way to tackle these questions?
It's a fair question from the point of view of especially in a country like India, where there are multiple needs and multiple there's a lot of basic needs that our society has yet to provide for a majority of the citizens. So it's definitely a fair question, and one should answer it. I think one way to say it, and this is what science has shown throughout its history, is that it is fundamental science that has provided the breakthroughs which have transformed society, and so I can give. In fact, sometimes when I also get asked these questions, I mention that 50% of the GDP of the United States probably depends on quantum mechanics. That if you didn't know the laws of quantum mechanics, then you wouldn't have most of the industries, most of the things that right now generate. I mean, look at what we are talking through this laptop, the lasers, the cell phones, the screens in our digital cameras, everything. This whole technology relies on the quantum mechanical phenomena. So before 1925 or so, when the laws of quantum mechanics were unearthed, you wouldn't have been able to even imagine how to have something like this, how to realize something like this. So it might have seemed that quantum mechanics is a very abstruse thing describing just properties of atoms. So who cares? But no, it is the investment in that curiosity that has enabled you to do things, and it continues to do things. And perhaps quantum computing will be the next another new paradigm of computing. And this again requires one to understand quantum information, quantum mechanics at a very deep sense. So this is not only something of the past, it continues. And in many fields of not only science, I mean, you mentioned specifically astrophysics and theoretical physics, but just before that, just even in terms of like even biology, modern biology arose from the fact, it was physicists, many physicists who, through the science of X-ray crystallography, which was used for understanding the properties of atoms, who managed to decipher the double helix structure of the DNA, and then the DNA and everything, all the genetic revolution. How did we manage to overcome many of the COVID vaccines that we have are products of mRNA, there are mRNA vaccines. And so without knowing these fundamental things of science, we wouldn't have had any of these advances that we take for granted, or the ordinary citizen takes for granted, and which has changed their lives, which changed people's lives. Yeah. So I think it's often shown that every investment in gives you 5 times that returns in terms of the knowledge that it produces and its utility, even though that may not be the reason that you are producing that. You mentioned astrophysics, so I actually gave a talk in some places about this recent thing where people were imaging these black holes at the center of this M87 galaxy and so on. So I was so the kind of imaging techniques that were used to put together the signals from half a dozen telescopes, radio telescopes across the world, and try to sort of piece together. I mean, it's like you have just a few pixels, and from that you're trying to reconstruct faithfully an actual image. And the kind of algorithms that were developed to do that imaging, to get accurate picture, these are the sort of things that are going to have other applications. So fundamental science, and especially in things like astrophysics and so on, pushes the frontier. And when you push the frontier, you have to push many things. Technology, you have to push your understanding of things. You develop new tools which at first sight have nothing to do with even the problem that you're attacking, but which will be useful in other contexts. The World Wide Web was developed by CERN as a kind of way to manage the large data that the colliders generate, and how to share that data in a very effective way with the worldwide collaboration of physicists who look at this. So this is always going to be the case. Once you have challenging questions, you will be pushing the frontier. And tomorrow it will be Facebook that will be using the image recognition algorithms or someone else to produce better ways of recognizing things. You take a picture and it's very blurry, but you use the same digital reconstruction techniques to make sense of them, or to sort of refine the pictures. So this is bound to happen. And similarly, I mentioned about quantum computing. I think we are learning actually that there's much at the level of quantum many-body systems we don't understand, and that's going to be another new frontier, which is where theoretical physicists and mathematicians, computer scientists, and so on will need to come together. So this, I think, more than justifies the investments that put in.
Indeed. I can use some of those points.
It's super intriguing how easily and how efficiently you were able to just point these things out, and it is extremely legible, or at least intelligible for any common person as well who is not working directly with science. So at this point, already we are past the time, but I would just like to put in some audience questions, if that's okay.
Yeah, sure.
So there were 2 or 3 questions that we were constantly getting, and I would just like to put those together. We've also received a lot of questions personally from the audience. So for instance, there's this one question which Panav and Akash have been asking, that how does one find their interest in a subject, or how does one get sure about it? Because sometimes you go towards physics and you like it, and then you see mathematics and you're also liking it. So how do you kind of balance between this, or find a middle path or something?
I think you should cultivate all your likes, and but at some point you need to also see what is it that you have a flair for also. There might be many things I might be excited by at an idea level, but then you start dipping your toes into the water and trying to see, if I start trying to think about these things, what is it that I feel I have a natural taste for, or somewhere where I think I can bring something new. I feel that I can potentially ask new questions and solve them. So that comes with time, and I think over your undergraduate years and even afterwards, and it takes different people different amounts of time to find that. I think you have to sort of get exposed to a lot of things, do many courses, and doing the problems, and doing lots and lots of problems. I think in whatever subjects you're doing, especially in the quantitative areas that we are talking about, like physics and mathematics, I think it gives you a sense for what are the things that you enjoy doing. Maybe some people will enjoy doing a lot with computational stuff, and there is a bigger role these days for computational physics, and it requires very non-trivial skills, and both in terms of algorithms and coding and clever ways to implement numerical codes, because that immediately allows you to tackle new problems. So you have to see what is it. You have to get a sense for what you feel you are really able to do very well at, and I think you should focus on that. But retain your interests, and who knows, sometimes you might connect something with something else. I was always interested in mathematics, but I knew that I wanted to mainly focus on physics, but then my interest in mathematics has come in many ways, and I have also sort of worked on things on the frontiers in mathematics. So it's in some ways many things can connect at some later point, but at the initial years one should focus a bit too.
Thanks a lot for this intriguing answer, sir. Yeah.
I would also like to ask some questions from the chat as well, and this one is a bit interesting from Mr. Altaf M. So he's asking how we quantize gravity. Will that complete the standard model? If you can, make us understand the gravitation concept in comparison with other quantization of fields or interacting particles. I hope that's...
This is, of course, one of the driving questions of string theory. And gravity seems to behave... indeed, the standard model is all the fundamental forces except gravity, and quantizing gravity in the same framework that you've quantized the other forces, namely this framework of quantum field theory, doesn't seem to work. I mean, people have tried it for 70, 80 years, and it has not worked. And there seems to be good reasons to understand why it shouldn't work. Gravity is tied up with the geometry of space and time, and usually when you to how to quantize space and time is a very it's a much more, I think, conceptually challenging task, and I think and so this is why I think at the quantum level gravity behaves quite differently from other forces, even though classically they all look gravity and electromagnetism look more or less the same. Okay, one is universally attractive, but the other has attraction, repulsion, but otherwise they are sort of similar, you might think. But really the deeper origins of the gravitational force being tied to space and time have made it much more, have really led to it having very unusual properties, and black holes and things like that are actually the signatures that of the very unusual nature of gravity. And so black holes, that's why, are very central to modern day investigations of the quantum theory of gravity. And they're also, of course, right now very important even in the classical astrophysics descriptions because of LIGO and Event Horizon Telescope and so on. But so black holes have been playing a very central role, and there are many theoretical puzzles associated with black holes that Hawking and others had raised, which I think string theory has been managing to give a very novel explanation, which seems to require that space and time itself are some kind of emergent concepts and perhaps not ultimately fundamental concepts. Of course, I think these ideas are still being fleshed out. We see it kind of broadly, but I think to have a complete description of this is still something that's under progress. So, but it is one of the very exciting things, and that's one of the areas my own recent research has been focusing on. So quantizing gravity, that's these are part of the challenges of quantizing gravity, to understand how space and time, our classical notions of space and time, can emerge from an underlying quantum theory.
So we are also having a huge number of participants who are attending this from the YouTube also, and we are receiving so many numerous questions. I would like Gautam to ask one question from there also. It will be good for them.
All right, then Naman, I will take that question. Okay.
Yeah.
So from YouTube, we heard this an interesting question from Melvin Varghese. What do you expect as a guide from a fresher who has joined for his PhD in theoretical physics?
So for a fresh PhD student, I would expect that she or he has has firstly a good understanding of the basics of physics, and then has not narrowed themselves too much. So by the basics, I mean like things like the classical mechanics, quantum mechanics, and statistical mechanics, and electrodynamics, and of course all the mathematical tools that come with that. So these basics, I think, if you have a strong conceptual ground, and the test for your understanding is, as I say, to solve problems. You should have done lots and lots and lots of problems. I think that's the only, and not routine problems, challenging problems from challenging textbooks, until you found problems that you can't solve, where you understand, then you forces you to think, what is it that you don't understand of the material? So that's what I think. Someone should have that basic solid grounding before, I think, really embarking on a PhD in something like string theory. Of course, sometimes that's why many places have a first 1 or 2 years of coursework. So if there are any gaps in your undergraduate education in some of these topics, this coursework or self-study also can help you to cover some of these gaps. But I think it's very essential to sort of know the foundations across physics very well for a PhD in string theory or related areas, because you will need at some point all of these concepts will enter in some way or the other.
Okay. So I think we could just finish it off with the last question from the Naman side, because we are actually quite constrained on the time.
Yeah, we are really sorry, sir, that we extended this a little bit, but we just like to ask this last question from you. If we missed out anything, if you have any ideas or any advice for as a parting advice for the young researchers and students, as well as budding graduate researchers as well. If there's anything that you think is something that is missing in the general context in Indian research area, research scenario, and also how you see this Indian research scenario flourishing over the next years, and how you think this should go on as a.
So I would say that to start with the last part, I think there are by now in physics at least a number of flourishing areas, flourishing research institutions, and it's only growing. And I think that each institution has a unique character, and it's a good time, I think, for people to seriously consider doing their PhDs in India. Of course, it's PhD. If you get to do your PhD in some very good places abroad, that's also an option you should exercise. But what I mean to say is that there are multiple very good options in India as well, and so you should explore them too. And I think it's only going to get better that way. Depending on the areas of your interest, I think you'll be able to find high quality researchers and institutions. The PhD period is a little bit of a difficult transitional period from being a student to asking your own questions and making sure that the questions you ask are solvable questions so that you can do your PhD in that. So you can of course ask very big questions. You have to have a balance between. I think you should have a lot of ambition and ask ambitious and big questions, but learn how to break the big questions into smaller questions, which are tackleable in the shorter time frame, so that you can build towards the bigger questions. So anyone who has that big passion for physics and wants to ask those big questions, try to cultivate that ability to break up the big questions into smaller questions, toy questions, which will build up your abilities and kind of flesh out the bigger question actually sometimes.
All right. Thank you, sir. So I will just ask Arun to take over this now.
So thank you, sir. Thank you for joining us today. It's such a wonderful session, and we have covered a lot of questions. All the questions, most of them have asked you are the questions we received at the time of the registration, and also the questions prepared by the research team of both the Zeroing and the Astro Kerala and this Shasthra Snehi. Thank you so much, sir. And I am welcoming Sri Bala, our senior board member, to express a word of thanks. Thanks.
My pleasure. Yeah.
Is it clear, Anna?
Yes.
Okay, fine. So, good evening, all. This is Sri Bala from Shasthra Snehi. So, right now we have been with a very famous personality listening to a wonderful interactive session. And I'm pretty sure that you people had a really good time listening to Professor Gopakumar. And now let me take this opportunity vested upon me to extend my sincere thanks and gratitude to Professor Dr. Rajesh Gopakumar for being with us and spending your valuable time with us in spite of having such a busy schedule. Thank you, sir. Thank you for being with us today. And
Thank you.
Yes,
and best of luck to all of you for your future studies and pursuing your dreams.
Yeah, thank you, sir. And now I also take this opportunity to extend my sincere thanks to Professor Ajit Parameswaran of ICTS-TIFR and Professor Anand Narayanan of IAST Trivandrum for their kind guidance and support throughout the coordination of the event and throughout the working of our organization too. And also to our presenters Gautam and Naman for carrying out the discussion in such a fascinating and disciplined manner. I also take this opportunity to thank the entire team of Zeroing In and Shasthra Snehi for your coordination and organization and making this event a successful one. And finally, to all our audience, both in YouTube streaming and in Microsoft Teams, for your kind listening and your active participation throughout the event. And also, as but not the least, I would like to extend my sincere thanks to each and everyone who have joined us with today. And we hope the same level of participation from your side throughout the entire conduction of the event. And please don't forget to participate with our scientific celebrations that is ongoing till now. So this is Sri Bala signing up. Thank you all. Thank you for joining us today.
Thank you, sir.
Thanks, sir.
Thanks a lot again, sir.
You're welcome. Thank you again. It was an enjoyable interaction, and I hope to see you all sometime.